Alright, so this is a demonstration about conductivity and what it means for a particular substance to be conductive. So here, as you can see, I have drawn a sample of atoms from just a generic set. So each of these atoms have 3 electrons in them, and these can move around inside of our atom. And then they also have a positive core, and that positive core would balance the electrons that are in each. So these would all have a +3 charge in their overall atom, and then these 3 negative charges to balance that out. We have 2 types of substances. We have insulators and we have conductors. And the major difference between those two is what happens with the electrons when they are brought together with a charge. Focusing in on the insulator, we can see that the electrons are always going to be attracted to that positive charge because the electrons are negative. But in an insulator, the electrons are not allowed to leave their atom. On the conductor side of things, though, it's a little different. The atoms don't hold on to their electrons as tightly and allow them to jump from atom to atom. Now, overall, this has a neutral charge because, again, these atoms over here have still the +3 charge as we saw before, and these still have the +3, but all of these electrons have moved over. So we see that this side is slightly positive and this side is slightly negative, but overall this sample is still neutral and our electrons have just gravitated towards this positive charge. So when we are looking at a sample, we want to identify if it has these charges, if it's a conductor or if it's an insulator. We know already that things like a piece of copper, like what I have here, is a conductor and electricity can go through this, or our electrons are moving through, because this is what we put in our walls as wire to travel, or for electrons to travel across. It acts like the conductor on this side. Now the wires are surrounded by a rubber coating which acts as an insulator and keeps the electrons inside the wire and not going through our walls and electrocuting us when we don't want them to. So we're going to look at a thing called conductivity. And we have identified that something is conductive if it has a charge and those charges can move. So in the example of our piece of copper, the atoms are not moving, but this is a metal. It allows the electrons to move around, so then our charged electrons get to move and it conducts electricity. Compounds don't tend to allow their electrons just to go wherever. They have ionic compounds with a give and a take of electrons and molecular compounds that have a share of electrons. We have some elements that form ions by giving away electrons or taking electrons in the example of Cl-, or we have groups of nonmetal elements that combine together and either give or take electrons. And this is charged. If these are allowed to move freely, it will match both requirements for conductivity, having a charge and allowing that charge to move. If these things are stuck in place, it still has its charge, but the charges can't move. So let's look at a couple of these things. So I have a sample here of copper sulfate. So right here we have a metal and a nonmetal that has been dissolved into a solution. And as you can see, it's a very pretty blue color. And we're going to take it off and we're going to read the conductivity of this. So I have my conductivity listed up on the computer here, and I'm going to take this little probe that has a little hole here. that reads the conductivity of our solution. So if I place it in here, we see that it instantly jumps up really, really high, meaning that these pieces in here are charged. So the question is, will this piece of solid copper sulfate, would it conduct electricity as well? And the answer is no. This doesn't conduct electricity because it doesn't move its charge. The charges are stuck with the particles, and the particles are stuck in a solid, so there is no movement. The same could be said for a sample of NaCl. If we have NaCl and we take the conductivity of it as a solution, we see that it too is conductive, but as a solid piece, it's not going to be conductive. Because again, our charged atoms of Na plus and Cl minus are not able to move when they're stuck into a solid. Brings us to dextrose, which is a type of sugar. And sugar is made up of carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen are all nonmetals. So to test if this conducts electricity or has charged pieces, we can dissolve some in water and take a conductivity reading. So I have some dissolved here in water. The conductivity of this is not very high. So it would make sense that sugar and compounds made out of nonmetals are not conductive. So let's bring this back to copper and this metal. And we know that the metal is arranged like this, where in a solid our particles are stuck, but they allow their electrons to zip around. The question that we need to ask is this more conductive as a solid or as a liquid? In our compounds, we saw that they were conductive as a liquid. Here, the real answer is that it is more conductive as a solid than a liquid. In the case of copper sulfate, the SO4, those particles needed to be able to move to get the charges to move because the charge was stuck on an atom. In the case of copper, the charges are not stuck on the atom, but are the electrons that are allowed to move. So, as a solid, it is more conductive because we have these paths, or freeways, that allow the electrons to get as close to the positive charge as possible. If this was a liquid, these particles would be moving all over the place and kind of blocking the path of our electrons. So, as a liquid, it's not as conductive because there's pieces getting in its way. So if we reference our periodic table, we will notice that things that are in here in the middle are metals, and they tend to be very conductive. And they are conductive for this reason, where we have electrons that are able to move. If we look at compounds that contain a piece from this side and a piece from this side, they tend to be conductive in liquid, meaning that they have a charge, but they need the liquid state to allow those charges to move. In a solid, they are not conductive because they are not able to move that charge around. If we look at compounds that are made strictly with pieces from this side of the periodic table, or the nonmetals, we see that even in a liquid, these are not conductive. So we can conclude that this is not none of these are charged particles. The question I want to bring up is water. Water is made from hydrogen and oxygen. And we want to know if it is conductive. So I have a sample here of deionized water, so of H2. So let's test the conductivity of water. So I have my conductivity meter. Let me get it out of the cleaning solution. And if I place it in the deionized water, we see that it really doesn't have a conductivity. So why can't you go swimming in Morris Reservoir when there is a storm coming? Well, Morse reservoir, just like our tap water or pool water, so tap water, is conductive. Why would this water be conductive and this water not be conductive? And the answer is simply that this is not just water. It is more similar to this solution or the NaCl solution than to the deionized water, because this has particles floating in it. It has some calcium, and that's that white scaly stuff that you usually get in your sink. It has iron, which is the brownish orange color that sometimes stains our bathtubs. It also has things like fluorine that we add for the safety of our teeth. So tap water is not straight water, and this conductivity that we are reading is really the conductivity of those ions, those charged pieces that are floating around and able to move.